Okay, welcome back to my programming in ARM assembly video series that I'm doing. And in this video series, we are continuing to expand our toolkit. We've already made a general purpose print function. We've made a general purpose ASCII to integer function. So in this video series, we're making an integer to ASCII function. So we're going in the other direction. All right, so in the previous video, we just laid out the foundation for what we're doing here. And I went through the roadmap that I have created for putting all this together. So now let's go ahead and jump into our code. All right, so first of all, let's get into the i2a.s file, the new stuff. And we'll start off by outlining what we need our inputs to be and what our output will be, so that when we're looking at this function, months or potentially years from now, there won't be any guesswork. So I'm going to say input, and we're going to say that R0 must contain the integer to be converted. So converted. So for example, 1, 2, 3, 4, or whatever it's going to be. And then also the as a part of our input, R1 must contain the memory address, which is like the pointer, the memory address to the variable, essentially must contain the memory address to the variable where we will store our result. And then as the output, we're going to say that the output R1 will contain the converted result. And that's probably not the best way to word that, because technically R1 will just be a memory address. So let me say it this way. R1, the memory address that R1 points to will have been updated with the result. That's probably a more accurate way. If not better, it's a more accurate way to describe what's going on. All right, so when we come into the function, we want to initialize. We want to back up the registers so that we're not potentially messing with anything that somebody that the calling function may have done. We don't want to stomp on any of those results. So we want to push those registers onto the stack before we do anything else. So let's push onto the stack registers, let's say R0 through R7 for now. Maybe we'll change that, plus the link register. And then while we're thinking about that, let's come down to the exit section and say that when we're done, and actually I am going to have to change that because I already see a problem with it, and say that when we're done, we're going to pop off the stack R0 and then R2 through R7 plus the link register. We could push R1 onto the stack, but we don't want to pop R1 off the stack, because otherwise when we return from this function, we will lose the work that we've done. So what we really want to do is push onto the stack R0 and then R2 through potentially R7. Again, maybe we'll change that, plus the link register. But when we come back, we want to make sure we don't pop R1 off the stack, because otherwise, again, we will lose our result. And then we will branch exchange to the memory address that's contained in that link register. And then after we push those values onto the stack, we're going to want to initialize some variables. Let me go ahead and just go to my roadmap rather than potentially making mistakes. Let me just go through the roadmap that I've already outlined, which again I know is valid, because I recorded the entire video series and then decided I didn't like it, so I'm redoing it. So as part of the initialization, we're going to move into register 2 the immediate value of 1. And this immediate value 1 is going to keep track of what the highest power is that's required in order to do all the necessary divisions. So in the case, if we just pass in the number 5, then the highest power of 10 is just going to be the ones place. If we pass in the number 17, then this will eventually become 10. If we pass in 127, this will be the hundreds, and then so on and so on. So variable or register 2 will keep track of that power of 10 multiplier. And then we're going to move into register 3, the immediate value 10. And again, that's just because we can't actually use the immediate value 10 in the division and multiplication operations. So we have to have that value stored in a register. And then we're going to move into register 4, register 0, which just gives us a backup copy of that original number, because R0 must contain the integer to be converted. But as we go through some of our steps, we're going to end up essentially destroying that number. So we want to make sure we have a copy of it so that as we do the next part of the operation, we can refer back to that original number. Okay, so now I think we're ready to drop down into our loop. And the first thing that we want to do in our loop is compare register 4, and remember register 4 is a backup copy of the original number, so let's just think of it as the original number. We're going to compare register 4 with the immediate value of 10. And then we're going to say if register 4 is greater than 10, then we want to do this division operation. And apparently udivgt is not part of the syntax highlighting, but I do know that that's correct. So we want to say udivgd, and we want to say take register 4 and divide it by 10, divide it by that power of 10 multiplier. And that will take it from, let me think about this, R4. Yeah, that'll take our number like 1, 2, 3, 4, and then that'll take it down to 1, 2, 3, and then down to 1, 2, and then down to 1. We're going to cut it down by a power of 10 each time we go through. And then we also want to multiply, if that number is still greater than 10, we want to multiply R2 by the power of 10 multipliers. So R2 equals R3 times R2. And remember, R2 is initialized as 1. So the first time we would go through this, it would be 10, then 100, and so on and so on. And then if we make it all the way to the end, we want to branch. If that initial comparison is true, we want to branch back to the top of the loop. Eventually, what will happen is this won't be true, and when that's no longer true, this won't happen, this won't happen, this won't happen, and then we'll fall down into the next part of the code. And we're actually going to have 2 loops here, so let's call this, let's just call it loop 1, and let's call the second one loop 2. Keep it nice and easy. But before we get into loop 2, we need to remember that since we have lost the value of R4, we need to restore, so we're going to move back into R4 the original number, because as we went through these division operations, the value of R4 was turned into something else. So now we're going to bring back R4, and so to sort of think about what we're doing with our code here from this example, if you remember this first loop, this is what we're accomplishing. We're stepping through our number, and we're just finding out how big of a power of 10 do we need. That's all we figured out. So in the case of 1, 2, 3, 4, we figured out that we went from 1, 10 to 100 to 1000. That's all that loop did. And now the second loop is going to do this step. It's going to isolate the 1, then it's going to isolate the 2, then it's going to isolate the 3, then isolate the 4. And each time we isolate these numbers, we're going to add 48 to it so that we get the correct ASCII character, and then we're going to store the ASCII character into the memory address associated with register 1. So let's walk through the next loop. And before I do that, I'm going to take a sip of water. Okay, so in the next loop, we are first of all going to compare register 2, which is our power of 10 multiplier, with the immediate value of 0. And then we're going to say if R2 is less than or equal to 0, then we're done. We've gone through we've gone through all of our numbers, and we don't have anything more to do. So we're going to branch to this label that I'm calling null byte, and we'll define that later. But as we're working through the number, that's not going to be true. So we're going to fall down into this next part of the code where we need to do these operations. So we're going to divide we're going to say make R5 equal to R4 divided by R2. And remember, R4 is the copy of the number. So if it's the 1, 2, 3, 4, we're saying take 1, 2, 3, 4 and divide 1, 2, 3, 4 by whatever value is stored in R2. And currently R2 will be 1,000. So R5 will contain the value, the integer 1 at that point. So then we're going to say multiply and then let R6 be equal to R2 times R5. So in the case of 1, 2, 3, 4, we're saying let R6 be equal to 1,000 times 1, because this operation will have given us 1 in this register, and then R2 hasn't been changed yet, so R2 will be 1,000. And again, if we refer back to up here, what we're talking about at the moment is this step right here. Multiply, let R6 be equal to R2 times R5. That's that step here. And so then the next thing we need to do is the subtraction step. We need to say take the original number and subtract out the result of that value and store it in a register. So that will be the next thing we do. Okay, so we'll go to the next line and we'll say subtract and let R4 be equal to R4 minus R6. So we take the number, 1, 2, 3, 4. My stupid phone thinks I'm saying something to it. We take the original number 1, 2, 3, 4, and we subtract out the result of that multiplication operation. So we've taken, 1, 2, 3, 4, and now it's 2, 3, 4, and then afterwards it'll be 3, 4, and then finally it'll be 4, and then eventually it'll be 0. Okay, and now we need to add to R5 the immediate value that we get by checking the ASCII character 0, which is going to be 48. So we're saying make R5 is equal to R5 plus 48. And once we've done that, we need to store that bit, that byte. We need to store that byte into we need to store the byte R5 into the memory address associated with register 1, and then we need to advance that memory address forward by 1 byte. And then we need to reduce our power of 10, so we need to divide R2. So R2 equals R2 divided by R3, and remember R3 is equal to the immediate value 10. So this is where we're saying now take 1,000 and divide it down to 100, and then we'll take 100 and divide it down to 10, then we'll take 10 and divide it down to 1, and so on. All right, and then if we've made it to this part, we just need to branch back to the top of the loop and continue everything again. So we'll branch to the top of loop 2. And once we, the exit point will be right here. So once we finally brought R2 down to the point that there's nothing left in it, we will reach our exit point, and we'll go into this section, which I'm calling null byte. And this just ensures that our ASCII, that the memory address pointed to by R1, after we add in all those ASCII values for our number, we will terminate it with a null byte. So we want to move into register 5 the immediate value 0, and then we want to store that byte R5 into register 1, and then advance that byte count forward by 1. And that's everything, actually. So once we have done that, we will just unconditionally fall into the exit branch, which means we'll restore our registers back to the way they were, and then we will be done. So it looks like we don't need to back up register 7 because we didn't make any changes to it here. So it looks like we just need 0 and then 2 through 6. So let's go ahead and change that to those values. And then if I didn't make any mistakes here, which it's almost certain that I did, but if I didn't, then we should be able to test this out. So let's write the changes, let's quit, and let's go into our main function and present the I to A function with some data to try out. Okay, so let's come into the start label and let's move into register 0, the immediate value 1, 2, 3, 4. And then let's move into register 1, the memory address of some label that I'm just going to call num, I guess. So that means we need to come up here into our data section and we need to create a label called num. And that's going to be of type ASCII, like that. Yep. And then we need to initialize this some way or another. The way I'm going to initialize this is as follows. I'm going to put in 10 zeros, and then I'll explain why probably in the next video. But let's put in 10 zeros. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And we might even want to put in an 11th. Actually, let's do that. Let's put in an 11th zero and possibly even a 12th. But I'll explain why I did that. But again, for now, let's just test this out. Okay, so we've moved into register 0, the immediate value 1, 2, 3, 4. We've moved into register 1, the memory address where we want our result to be stored. So now let's branch and link to our I to A function because we've preloaded registers 0 and 1 with what the I to A register or the I to A function needs. So let's write this out. Let's quit and let's just see if we can assemble this and link it without getting any errors. Fingers crossed. And of course not. So, oh, I already see the, yeah. You can't, I make this mistake from time to time. What we actually need to do here is load into register 1 the memory address of num. We can't move because that's just not the right operation. So let's write that, let's quit, let's make clean, just to clean everything out. And let's clear the screen and let's make again. And right now we won't see any result on the screen, but by running this, it will let us know, do we have a seg fault or do we get stuck in an infinite loop? Either one of those things is bad. And it runs, it didn't seg fault, it didn't get stuck in an infinite loop. So that means that we don't necessarily know that it's working, but at least we don't have any obvious catastrophic problems. All right, so that's going to wrap it up for part 2. When we come back in part 3, we'll actually take a closer look at this to make sure that it's actually working how we want it to work. And I'll explain why I put in that long list of zeros in that variable. If you made it all the way to the end, thank you so much for watching, and I hope you'll come back in the next part.